So as I said, we want to take a look at the project because this is it on the mic? Okay, because I can't hear the feedback, so I'm not sure, but if on, then it's on. So let us go to this project. So this is, I think this is the one of the most important assessment in this course. I mean, of course, in terms of grading, I mean, of course, exam is important, but I would think this is the most useful for you because that is how you learn things, right? Because of course, exam you also take revision, right? But still, I guess that would be the idea, right? Just try to ask you to force you to work out projects, and then good thing is this is you can consider as an open-ended assignment, right? You can do whatever you like, and then to just want to remind deadline. Oh, is it the old one? Sorry, I think it's the old one. I will change it, but it should be. I think I uploaded the wrong one, but the deadline will be the 1st of December, the very last day of the because I think this is the old version, but I uploaded the latest version because I don't know why. I mean, I created a new version, but I don't know upload the wrong one. But they're almost the same thing. So the thing is, you can do yourself or do it with your classmate. Did I share the screen? Yeah, I share the screen. Yeah, and MO6, okay, and because you can always do your own work, so I just don't want to entertain any complaint about your group member not working. If group member not working, you can just simply do it without him. Okay. So you just write a short report and put your name and ID on the first page of report. And each group member, okay, have a page limit of 1 page of A4 paper, 2 sides. Okay, if the two members group, then you have four pages. Okay, 2 A4 paper. Okay, and just it's just a maximum. Okay, so if you have 6, you maximum group size, then at most you can write 12 A4 pages, right? Or 6 A4 papers. Okay, and as a standard, you submit to the very guy before you submit, and you PDF form. So this is the way you would be recommended to how you work out your report. I mean, just you just explain what you're studying, right? You would put as a business report, you would put your conclusion up front, right? What are the things you want to do, right? And you probably want to analyze what they've been doing and then try to pick up the things you like, okay? And try to make sure that your report is professional, right? It's not kids friendly, but business friendly. Okay, try to avoid emoji or whatever. I mean, unless your thing is emoji that is attractive, otherwise try to make it professional. And you may include everything you want to say in the appendix, but it's not included in page limit. And you put your data source or technical appendix or the source file into appendix, ship it together. Okay, and I would consult them when I need it. Okay, so that would be the thing. Okay, and probably some of you may ask, how can you brainstorm? I give you the example of several years ago. These are all the work that are considered to be B+ or above. Okay, I mean that means that above median, right? So that would be I mean, of course you can probably tell which work is A or A- or B+, but I'm not going to tell you, but you have some idea. But say for example, this is studying whether the zodiac sign is scientific, right? Just I think this group is very into this kind of stuff, right? So they would just look at doing some sampling. Okay. I think they just from the data that we tried from somewhere else, and try to look at the data and do 3 pages. I mean, this group has 6 people, but they only do 3 pages. Fine. I mean, you don't have to. I mean, it's below the bar. I mean, because they can write 6 pages, but they just write 3. That's fine. I mean, you don't have to use up all, right? As long as it look nice, right? I think this very colorful thing is good, right? And also they make the things later you will learn, right? They would do some hypothesis testing, look at some data, do some estimation, do some box plot, right? And another type of question, right? The good thing is it's very clear, very clear what are the hypotheses, right? Because they will try to ask 4 questions, right? Is this specific element perform better than the others, right? Is it water better or fire better or air better, earth better? This kind of stuff. Okay, so this is a kind of the thing. I mean, you can take a look. I mean, probably I can go over the other one with you. I'll just randomly pick one because. So this one, just 2 person. They do 2 pages. Okay, and I think the reason why they don't only do this is when 3 years ago I had this class. I think 1 person only 1 page, and I think I got the feedback said, I mean, I should allow a little bit more. So I allow 2 sides or 1 A4 paper. So that's why they do 2 person group. They do a 2 page. So this is try to get some estimate on the population, right? Although it looks simple, but it's very clean. So they look at the population, try to do regression. So it's very simple report. Okay, so just pick whatever you like. Need not be business related, but I recommend you do business because you're a business school student. But anything will be fine as long as you apply what we learned in the class. Okay, is that okay? I hope this give you more clear what you should do. Okay, but it's just a semester long assignment, right? And you condense it into 2 pages of a report. I mean, for each of you, right? At most 2 pages. Okay, and remember, just try not to fill 2 pages with tests. It's rather boring for you and for me, right? And then better to make it look nice, visual appealing is very important. Okay, is there any question before we start? All good? Then hi, yeah, good. Make sure that the Zoom is already there. We have the so today and also I think Friday, probably we should able to finish probability. And here we don't have any Excel for this one. But after this, then we probably have assignment. Okay, assignment will be released after we're done with this one. So for probability, that I guess if you have done math in the high school and you would have heard about it, at least done some about it. Okay, since we are not a math class, so I would not expect you to able to handle a lot of probability problem, right? But we will try to give you the foundation what we are doing, right? Because this build the foundation for the next topic, random variable. Okay, but we'll just give you the idea what a probability gives you the solid foundation, or at least understanding what's going on in the probability. Okay, the level of difficulties will be, you can see, will be from your assignment and also from the slide. I mean, of course, you can go very deep in probability, but we will just give you some very basic definitions, and there's some basic rules that we will be using. Okay, but most of them is rather technical, so it's a rather math class. So just pay attention. If you don't understand, it's normal. Just check the example I give you, and if you do the assignment, just try to figure out what's going on there. Okay, of course, it's okay to talk to your classmate, discuss about the assignment. Of course, You may also, some of you may go to the ChatGPT or AI help you do it. That's fine, but you have to understand what's going on, right? Because it's important for you. So probability. So what are we doing here is, remember why we do probability. One of the reasons is probability modeling is important business, right? Because you try to model the, say, how many customers arrive and you make decision, right? And these are the things that you would require probability, right? Because if something is not about the future, then probability is the right language to describe how things will realize, right? Look at the Hong Kong Observatory, right? Every day they look at the probability of rain, probability of sunshine, and so forth, right? The business is involving future decision. The probability is the right language to describe something hasn't happened yet, right? Or even look at the criminal thing, right? You assign probability as well, right? So reason, I guess many of you may have noticed, right? The headline is the JPEX, right? JPEX, right? It's about a very famous guy being got in the police station, right? And then probably you would try to wonder how likely he's a fraud or he know the scam, right? There's some probability, right? It's about the past, right? Also, you can talk about probability, right? Because actually what is the court system, right? Is you were given evidence, you try to see whether the evidence will tell you the probability that he's willingly or knowingly committing crime, right? So that's about probability, right? We assign probability to the event in the past. But anyway, so let's get started with some basic terminology, okay? So define probability, we'll start from the classical approach. So indeed, the probability we will talk about is two approaches. One is from empirics. Probably can decide from data. Okay, that's how we define from data. Later we see it's called the relative frequency. And we will be working on the other approach is called the axiomatic approach. We define from definition. Okay, we don't rely on the real world, so we detach from the real world, right? Just like how we learn addition in the kindergarten, right? When you a baby, you learn how to count 1, 2, 3, 4, 5, right? And we learn add is just putting things together, right? But later we abstract them, right? Add it means a number line, right? Add it just means go forward, right? From one number to the other, right? So that is the idea here. We will try to learn something from very concrete example from the real world, and we abstract them from math, and that is how we derive a lot of the rules, and that is where the you learn statistics, right? That's why people would spend 4 years in the stat department to learn those things, right? But of course, we just have one class or at most 2 classes, right, to cover this. So we have to be very abstract. So or very quick should be, or to be in high level. So let's start with the low level thing first. Let's define random experiment. Okay, that is how we define probability from the real world. We consider random experiment is something that we know something will occur, okay, and we know what things might be possible, okay, but we don't know which one will be. So we will be surprised something actually comes out, which is very unlikely, but we're not surprised that it actually comes out, right? So, and it's a random experiment means that by the experiment means that it will be happening a lot of time. You can repeat, or at least potentially can be repeat. And just like toss a coin, roll a die, you can repeat many times, potentially, right? What is not random experiment is potentially saying about whether we have 2 moons in this universe, maybe 3 suns in the galaxy, or the random experiment is not like how likely we have another typhoon last week, right? That has been happened, it cannot happen again, right? So something is once for a lifetime, then probably you can't do random experiment, okay? But something potentially you're able to repeat, it's called random experiment, because we rely on data, right, to define this, right? So that's why I have to be able to repeat. And we define in something that happened from the random experiment is called outcome. Okay, and if you toss a coin, head is an outcome, tail is also an outcome. If you roll a die, the face value is being 1 is an outcome, right? Same as 2, 3, 4, 5, 6. So that's outcome. Okay. So we start with random experiment, and the outcome is just something coming from that. Okay. Do remember that repetition is an important idea of random experiment. Okay. And that's the no surprise. Okay. But I mean no surprise means that it will be made precise when we talk sample space. Okay. But let's consider first thing before talk about it called event. Event is a collection or a group of outcomes. Okay. And usually event is something we care instead of outcome by itself. Right? Suppose you roll a die, you want even number to comes out. Okay. And even number is event because it consists of 3 outcomes, 2, 4, and 6. Right? For example, that example you might care is rainfall. Right? Rainfall can come from 0 millimeters up to like any positive number. Right? And the event you might care is whether the rainfall is more than 100 millimeters per hour. Why? Because that is a black rainstorm signal. You don't need to go to work. Or it says more than 50 or less than 50, right? That is where you care the rainstorm, red rainstorm, then you don't have to go to study, right? So that's the thing you care, right? So the sample space is an event that contains all possible outcome, okay? When you say all possible outcome means that we know what are all possible thing, right? So that's why it's important, right? Because here we need to know what are all possibility, what are all possible outcomes. There will be no outcome that will surprise us. The only thing that surprises us that is that actually that outcome comes out, okay? But there should be no surprise on that outcome is really possible, okay? It's in theory that's possible, right? So that is the thing. So that's why the tossing a coin, there's a there will be sample spaces head or tail. Okay, it can't be say I toss a coin in the mid-air become a rabbit. Okay, comes a rabbit. No, that's not possible. There's no magic there, right? Toss a coin, it must be either head or tail. Okay, you cannot toss a coin, come out a ball, right? Or come out an explosion. That's another thing. Okay, that can't be like this. Roll a die. Okay, it must be 1, 2, 3, 4, 5, 6. Right? I guess in the old day there's a movie like the gambling movie, right? And they roll a die, right? And they roll, and then they open the die that become a sand or become something else, right? Right? Those kind of crazy movie. I mean, that is not allowed in our model, right? If you have to have that happen, then you have to be in the sample space. Okay. So we have a complete description of what will happen, right? So that is a random experiment. Okay. So now we have defined random experiment outcome, event sample space, that we can define probability event. That is called the classical definition. Sometimes you learn more technical, that is called the frequency list. Why frequency list? Because it's defined as a frequency, right? Frequency, remember we learned in the first class, is how many times it happened, right? It's a count. And suppose the random experiment we repeat many times, right? And probability is defined as a fraction where the denominator is how many number of experiments you have done. Okay, I think there's a grammatical mistake here. Oh, sorry, I didn't share the screen. Oh, I mean. Hold on. Something weird thing happened. I don't know why. Okay, green actually sharing. So for our classmate, actually, we are on the probability slide. I'm sorry, I didn't notice. So we cover random experiment, outcome, event, and sample space. So the probability is a fraction where the denominator, I mean, as a typo, a number of experiments. That's typo. So how many number of them are actually conducted, right? And the numerator will be how many outcome that favor the event, right? So suppose make it simple, okay? We just toss a coin. We only have head or tail, okay? And if we say a coin is there, right? Roughly you have a 500,000 a head, 500,000 tail, right? So how do we define probability? For head, will be 500,000 as the numerator and 1 million denominator, right? That's 1/2. Okay. So suppose the coin is unfair, right? We will say suppose all of them is head, right? You say, or what we learn is like the coin is like big coin, both sides head, right? So always head, right? So that would be 1 million over 1 million. That's 1. Okay. So by the definition of the fraction, it means already probability must be between 0 and 1, right? There's no meaning about probability is 2 because it's a fraction. There's no meaning about probability is negative. Okay. So that is the idea. That will be, we will use this kind of fact to define our axiom. Okay. So that will later we'll talk about actually the axiom, what we discussed will be all consistent with this classical definition. And we will extend more because we want to use the definition from math to derive a lot of formula here. But everything will be what we learn, generalized version will be consistent what we have done. Because we don't want to do experiment all the time, right? To do the calculation. But that would be the idea. Okay. So just to repeat, because it's very important, there's a classical definition, is you repeat many experiments, probability will be just ratio. How was a proportion that or relative frequency, right, of that thing would happen, right? Is that clear? Okay. So I think you learned it in your high school already for this one. Okay. Then we just give an example. Okay. This real quick example is rolling a die. We have a 6 face dice. Then one's outcome, 2, 4, 5, 6 also outcomes. Okay, because we just roll once. And the sample space is 1 up to 6, right? Because that is all possible outcomes. And event even number involve 3 outcomes, 2, 4, and 6. So probably those who haven't learned set theory would be wonder how I write things in this way. Okay. So this is the way that all the modern mathematics being written is called the set theory. The set theory would be saying that a collection of items would be represented by a curly bracket, and each item will be separated by a comma. So this is an object we actually call set, or SET set, right? And set consists of, here we have a 6 element here. Each element will be separated by comma. Okay. And for those who know, will be straightforward, but you don't know, then it's not straightforward. But that is the standard way people use it. And for those who know, right, because this is how mathematicians write things since the beginning of the 1900, right? Everything is start from logic, and logic from set, and set to build up everything from a set language, right? Actually, they prove using set theory proof why 1 + 1 is 2, right? I mean, but anyway, it's not our class, but they basically just like the modern mathematics, everything is starting from all this, and then later you see the set operation, union, intercept with the logic or not and this kind of thing. Okay, and these are consistent with the modern electronics, right? The semiconductor, those kind of thing. But anyway, that is how we define event. Okay, we write a group of stuff. Okay, number E will be a collection of outcome that is even 2, 4, and 6. Odd will be also a collection of number 1, 3, 5. Okay. Large will be 4, 5, and 6. Okay. Here the probability here is coming from what? Coming from our idea we're actually rolling a fair die. Right? We roll a fair die. Look at how many outcomes that are even. You would expect half of them. Right? Or if you roll 6 million times, you expect 1 million for each. Right? So for E will be, as the denominator will be 6 billion because we roll 6 million times. And the 3 million times actually is 2, 4, and 6. So it's 3 over 6. That gives you one half. Same for odd number. Right? The 3 millions of 1, 3, 5 and 3 million of 4, 5, 6. That would be the idea. Okay. Do you know that this probability we have coming from repeating our experiment? Okay. And you can do it at home if you want to try, but that would be the meaning of probability. Okay, I think they updated in this way on the right hand side. So another one we want to introduce you called the Venn diagram. It's also a free of set. Okay, and this is usually how you try to understand the operation of set. Okay, so it will be the whole sample space. Okay, and we have even number, odd number, or large number. Okay, why in this way you will see odd number involve 1, 3, 5 is a green circle. The E will be just even number 2, 4, 6, and large will be 5, 4, and 6. So this is the way to represent how different events are related. Okay, later we will use this. Okay, to tell you. Actually, the next slide tell you what are the intersection, what are the union, this kind of problem. Okay, so very quickly, let us continue. So they changed the new style, so I need to familiarize myself with this system. Okay, so here we have a rolling a die twice. Okay, so this is how you try to understand the understanding the sample space idea. Suppose you roll a die 2 times. Okay, rolling first and second. Okay, I'm not rolling the die simultaneously, or you have 2 die. I know which one is 1, which one is 2. Okay, it's not like I have a cup and I roll. I don't know which one is 1. Okay, I know which one is which. Okay, and that means that the outcome of this can be represented by a pair of integers. By pair is all the pair. Okay, so which means that 1, 2, and 2, 1 are different. Okay, or you can consider I roll the die twice. Right here I said roll the die twice. Right, it's not I have 1 die I roll twice. It's not 2 die I just close my eye and throw it. Yeah, then I cannot tell which one is which. Okay, here is important the order. Okay, that means that the sample space I have is 36. Okay, and because of you have 6 for the first die and second for the 6 is 6 times 6. Okay, we'll talk about how to count it at the very end of this class, with next class. But you can imagine why it's 36 is just like you can put them in a table, right? So you put them in a table where you have 1, 2, 3, 4, 5, 6, and you have 1, 2, 3, 4, 5, 6, right? So each entry represent 1 outcome. So that's why 6 times 6, right? And that is very simple, a sample space, right? But you can imagine if I have rolling the die 3 times, the sample space become how many of them? You have 216, right? Around 200, right? I don't need you to know the number, but you know it's about very big, right? If you roll 10 times, then it's a huge number, right? But we will talk about how to simplify this sample space next class. That will talk about random variable. That will be something we talk about next class. But let's not do about simplification. We start from the beginning, okay? And the event that 2 die, sum of 2 die less than 4, actually refer to 3 outcomes, which is 1, 1, 2, 1, and 1, 2. Okay. Only you have to note that this is they're different. Okay. And if the die is fair, then the only 3 outcomes of 36 is 1 of 12. Okay. So that is how you will be using. Okay. I know that if you are new from the probability, that would be hard for you to familiarize yourself with the language. But don't worry, we will be doing this again and again, and you also do the assignment. Okay. For those of you who know it, this is very boring. I'm sorry, but just have to make sure everyone on the same page. Okay. So let's, as I said, everything is in terms of set theory. So that's why the set language will be important. Okay. And the idea of operation on set is actually the daily language of, we call and or and not. Okay. Because we want to talk about this event and this event happen together. Right. We want to talk about probability that, say, what is the probability of even number or large number when roll a die, right? Or when they ask what probability of even number or large number, right? So this is the daily language, and how do we translate it into the operation on the set, right? Operation on the event, we have to use and or not. It's interset, union, and complement. If you learn set theory, that will be natural. But don't worry, that will be something you, this operation are something very familiar, or something actually you learned in the kindergarten. Okay, so this operation is something very simple, so don't worry. Although I use a fancy term, but it's not very fancy. This is the way that people use it. Okay, it's and or not, or something very simple, so don't worry about that. Okay, I know a lot of terminology, but that's the only way we can proceed, right? Because this is the way people use it. So interset is very simple. It just collect all common element. Okay, and because both are true, right? So you have to be common. So for example, you roll a die. Okay, you have event on and last, which we covered last time. So you want to ask, what is the event that is E and L? What is the, we want to later want to say probability of even number and large number. So even and large means that you have to figure out what are the common element, right? First one, look at the E. The way to do the algorithm is going to all elements in 2 sets, right? Going to everything there in E and L and see whether they have common. So is E appear in L? So 2 appear in L? No, it's not. Right? Is 4 appear in L as well? Right? Yes. So this one is yes. Is 6 appear in L as well? Yes. They're common. And 4, yeah, you don't check. 5, no, not really. Right? 6, yes. So that's why you have 4 and 6. That's how you get E and L. Is that clear? And then we use another color to denote the O and L. Okay? Let's check again. Is 1 appear in L? No. Is 3 appear in L? No. Is 5 appear in L? Yeah, we'll take it. Maybe a below, right? Take it. Yeah. And check again. Is 4 appear in O? No, not really. 5, you check. 6 is it? No. So that's only 5. Okay. So it's just grabbing the same thing, right? From the 2, right? So that is nothing, right? Picking something in common, intercept. Okay. Repeat, it's just picking something in common. So it's really easy to understand this if you consider the case of Venn diagram, right? In a Venn diagram, it's just where the intercept, right? The common overlapping area, right? So in this case, E and L, if you draw the Venn diagram, 4 and 6 in the middle, right? The overlapping area is called the intercept. Is that okay? Is that okay? Any questions? I mean, if you know it, it's very trivial. But if you don't know, it's completely new to you, then you have some time to digest. Okay? The union is something before common is just like finding the common factor here, right? That's like HCF operation. The union is OR, so it's more or less like finding the LCM idea, right? Common multiple, right? Lowest common multiple, just pick up everything there, everything in A and B. Okay? So suppose you have this, again, a sample space, EO and L. So how to find E union L is we want to figure out the outcome that is either even or large. How do we do about it? We just copy everything, right? Basically very simple. What are what element in E and what element L in L? We just copy, right? We have 2, 4, and 6. In addition, we have 5, right? That's how you write. And probably one of you might ask why I don't write 2, 4, 6, 4, 5, 6, right? That's the simplest, right? Why don't I write that? Yes, you can write that, but in the theory of set, if you repeat itself, has no meaning. Okay, so this is same as the repeat itself, the same thing. You just write this because they're the same thing in the set theory. Okay, in the set language, it's like if something, the same item repeat itself, the same. So you don't need to write it. You just need to write a unique element there. Is that clear? So just copy, just combine, or if you look, you're a computer scientist, your program is concatenate, and you need find a unique one, right? And same as O union L, you just get all of them, right? So it's nothing deep here, right? Especially when talk about the Venn diagram, right? If you draw a Venn diagram, then basically you just list just every element there, right? Nothing new. Okay. Now is remember this is or, right? Union says or. A or B, right? You can read A or B, right? For our purpose. And complement is the English letter means not. Okay. Basically, just everything but. Okay. In terms of English, right? I think in the old days, there's a very famous song, everybody but you, right? Like that one, right? That's the only I know that song because I only listen to that tagline. I don't understand anything else from that song. Okay, I think a Korean song, right? Anyway, it's everything but that. Okay, so we have an element 2, 4, 6. All right. So everything but E is what? Look at the sample space here. We just cross out what is in E to get E complement. It's just like you told 4, 6, take out 2, take out 4, take out 6. That's what left 1, 3, 5. Is that clear how we get that? Not is something not there. Okay. Okay. This 1, 3, 5, what do we get? You get take out 1, 3, 5. Okay. That OC, you can do it by yourself. It's 2, 4, and 6, right? Is that clear? And I think you can see why how we get L 4, 5, 6. Not large, it's small, right? It's 1, 2, 3. Is that clear? The 3 operations. Is that okay? So that's how you see E inside, not is outside. Okay. So maybe I can talk about this because I think this is very simple. Okay. So this is mutually exclusive. Okay. And we can use our idea and to denote what do we mean by this. Okay. Mutually exclusive means they cannot happen at the same time. Okay. So the definition is the interset is empty. This is called the empty set. There's nothing there. There's nothing. So there's nothing in common. Okay. What's mutually exclusive? The idea is, for example, if you are now in CHK, you can't be in Hong Kong U at the same time. Okay. So for example, a boy, is dating a girl A, and he might also dating a girl B, right? That's possible if there is a good time manager. However, at a particular point of time, he can only date one girl, right? If otherwise 2 girls are there, then they will fight, right? So it must be the case you can only either date girl A or girl B at a point of time, right? So dating girl A will be mutually exclusive with B, right? So it can't happen at the same time, right? I mean, assuming they talk together, then things will explode, right? So that assume that would be happening, right? That's the case. So do note that mutually exclusive means that they can't happen at the same time. It doesn't mean that one of them will happen. Okay? It can be both false, right? Because go back to the example, right? The boy may be dating girl A and B are mutually exclusive, right? But he may be dating girl C, right? Not A and B, right? Maybe girl D and E and F and G. So it can be mutually exclusive, right? And you are in CHK and Hong Kong U, they're mutually exclusive, but also you can be in Harvard. You can also be in Cambridge. You can also be in PKU, right? And you can be anywhere in the world, right? Other than this place I mentioned. So this is what we mean by mutually exclusive. Okay? So maybe I cover one more, then we'll break. So very quickly, because they are very simple. I cover this one, and then we'll break. So this one is called exhaustive. Exhaustive means at least one of them will be true. Okay? So this is called union of them, the sample space. Okay, at least one of them is true. Okay? So, for example, there's a very famous commentary when you look at soccer in Hong Kong. Okay, but probably you guys are young, but no one more soccer anymore, I guess, right? And what happened, there's a penalty kick. Okay, the commentator will say, now is a penalty kick. There will be two possibilities. One, the goal is in the net. The other is not. Okay, you know it's a tautology, right? But it's always true, right? It's either they're in or not in, right? And what happened also in other cases, probably now you don't see it in the TV show, right? Often there's a girl, okay, who is sitting lonely at a table, holding a flower in his hand, and she will say, putting a pedal of it, say, he loves me, he did not, he did not, so on and so forth, right? And that will run out of the pedals anyway, but is looking at exhaustive, right? Because either he loves her or he doesn't, right? So that would be exhaustive, right? Because it exhausts all the possibility there. Okay, so let us have a break of 15 minutes. What's the time now? 10:20. So we'll resume at 11:35. Yeah, that's the break.
Yeah, that's how you do it.
Yes. 咪逗號，即係話 E 係等於 O， 呢個逗號係另外一句詞嚟。啊。
我知道好人有反正。因为我跟着他那个班满了，然后我就去了那里，到时候我很想上这节课，然后那个没有，我就直接跟他当面讲说，我想说是能当上这个课，但是好吧，你破那个就是我往前坐，我放前面这个。
She's just not replying. I made it. So I think
So I'll be using the e-reply to collect information of class attendance and participation. You reply. So because now the job is over, so I think we should start doing that.
no with it.
Any question, let me know. That is trying to the U project trying to get you some to get you to write down what you don't know, and then we can discuss a little bit. 即係話一係 A 又 B 度發生咯，冇其他可能。即係話如果係一係。
I don't know. It's like,我哋第一次咁樣用，因為我都唔識聽，我都唔知啊。你 P 一就係我咁做嘅，你做我都介紹你哋第一班係個小白鼠嚟嘅，小白鼠，你真係小白鼠。哦，你上少一兩堂，我哋真係缺少得太多，我覺得，因為只會 report 俾上，如果你唔想嘅超過，我哋聽，因為通常呢個有前期嘅匯報有係喺香港出面追究，所以我要對今年打 check 咯，我 check 嘅真係今年我 check 嘅係跟住消失咗。我係未到，我先下大家我下面有嘢，喂。Well, that's true. Bro. I'll take it. You know what? Space 大家即個 space 都係冇識嘅咁樣。係即係話有 A 個身份就咁大問題。A 我發生大問題，其實擺人嘅，跟住嗰啲開始入線。非常都係一樣譬如話呢個 B 跟呢個 even 冇緊啲加埋你都未晒，你會真食三咁就做。第一次我去打啲啦，好真嘢係咁嘅。
社交可能好多咩research 定乜鬼嘢，有咩問題發生喺打機嘅？咁我先計㗎 business as 佢喺 UGEB 有個 chemistry 嘅，high five grade 嘅，跟住中嘅 one grade 嘅。我有試睇嚟教 high grade 個 project 係點樣進行嘅 criteria
你睇到我係啲咁就我哋有嘢，佢將啲必須係標零嘅，買嚟個溫比溫，嗰啲咩產品好意思啊，大家食佢，你食個高質我冇理由話我哋幾多分㗎，即係你一樣嘢特別優秀嘅，即係你當咗我係 B school 嘅，然之後我係你個老細或者係暫時老細或者暫時或者大人，你點樣 sell 嗰個嘢
？OK，
對，我睇佢，呢樣好啱你喎，冇問題。多數都做得正，好似即係都係咁嘅。
OK，收到。
即係假如你係能作咁啊，你 sell 個嘢嘛，sell 咧話純粹就單嘅，
唔想做㗎。
係咯，交數交咗幾多係咯，如果唔係塑膠嘅，我用100蚊買佢真係幾搞笑。
呢一你長嘅寫冇樣係盡，佢係啲人買啲食品。
有冇黃書？
我點解差嘅？我試過試，呢樣嘢。阿林啊，阿林啊，咪有邊個 represent 到
GPT 嘅
晒咗，有定啱都還有冇得？即係講我哋
呢個就係 M.Phil
我都唔
唔係我之前識做嘅，呢啲係啊，佢哋題目直接嗌名，然後就
會中意用嗰啲
我應該要
我哋係順其自然呢個。另外一個係我老邊都用我呢
已經唔算係啦，即係話我哋太遲啦，出年4月3日。
咁啱
我最而家係應該知。他拒絕你的。
實際上冇得大分別。我幾隻都好貴嘅，就係冇分別。我買咗幾隻都係。係呢個幾個問題。我哋有個好得意嘅贊助啲人咧，有個數嗰個，佢爭講數嘅。我精力睇得多兼我有讀住呢個呢啲咪特別叫咗一個批咗，你要爆假嘅，我哋你要專業有，譬如你小或者做咩當嘅一個領袖嘅，即係不合法嘅做得哦，係個咩？應該唔係咩？佢哋 SEP 嘅即係乜鬼嘢？死亡嘅WiFi。Already 有呢個咩嘢？呢個 Bluetooth 你負責點負責點？但 Bluetooth 嘅唔好處就係佢雖然係大佢大個，但係出嚟。
我也覺得，我以為你才奇怪。
對。我有啲正常講嘢嘅兩蚊佢。
你個 iPhone 有這意思？
我之前係聽翻咗，我都係啊。佢特色地㗎嘛，用係啊，我哋用。就轉咗 MX 呢個3
然後呢，有人他在一個人買，
So I guess I will because time, well, I'll end the thing, okay? So we have 63 people join. That's very good. So I think
我真係唔記得咗，得閒都要去。
let me I'll end, but how do I do that? End. Okay. I end it and I look at the how do I look at the report? Let me see.
Wow, okay. 其實呢個答案。
Okay, this first one everyone knows is today is Wednesday, so it's good. So most of you can follow, and one of you think it's very difficult. So I recommend if you find it difficult, talk to the TA. Try to see if things can be helpful. Probability, so everyone knows we're talking about probability. Yeah, but I don't think I talk about how to present data today. Yeah, I think I covered this so far. That's okay. I guess people are probably so far. I think it's about today as well. That's today. What do we have for the last question? I don't know what's that, but okay. So I guess that's good. We can go back. So today we just asking harmless question, right? So next time probably I will try to ask a real question to see whether you understand or not. So don't worry, it's not really marking your thing. So I mean, I just try to gauge whether you get it or not. Okay, also this attendance thing is not really trying to harm you anyway, but trying to see if you are absent from the class for no reason. Probably our TA will send you an email to see if you're okay or not. Okay, not to say but at the end of the day, we try to adjust the participation mark, then probably with some adjustment, but otherwise it should be not particularly issue. So some of you actually asked me during the break again what's the difference between mutual exclusive and exhaustive. Just to remind you, mutual exclusive means if one happens, the other doesn't. Okay, doesn't mean it can be both of them not happening. Okay, we just rule out they can't happen at the same time. Okay, the only thing we said about mutual exclusive means that they can't happen at the same time, right? Because there's always 4 possible cases, right? Both of them happen, both of them do not. A happen, B do not. B happen, A do not, right? So that would be 4 cases, but mutual exclusive means that it must be both, right? And exhaustive actually means it rule out that both things can't happen, right? Because it just rule out one thing, right? It is impossible you have none of A or B will happen, right? Either A happen, B happen, or both. Okay, that means exhaustive. Okay, and usually you just not talk about 2 events, but we're about a list of events or group of events. We talk about whether they are exhaustive. So why we would care this later you will see, because this is something very useful. There's some rule that in probability related to this, and the more importantly is when we say events are mutually exclusive and exhaustive, that means partition. Okay, and they're the same meaning. Okay, partition means there will be bunch of things that are mutually exclusive, exhaustive. Okay, and that means that the group of the event, there will be one of them will happen, and exactly one of them will happen. Let me repeat: there will be one of them will be true, and exactly one of them will be true. Okay, so that is same as I have a cake. I cut it into disjointed pieces, right? There can be both of them will happen. Is that okay? Good. So this idea, the sample space, we call partition if everything is non-overlapping. So it'd be good to go to example, because this is how you learn from definition, right? Always do examples. Same as how you do all the math, right? You go to math department, right? You do definition, you do example, then you will see whether you understand the logic or not. So I have an even number, odd number, but now I have another new thing. It's called prime number, right? And it's a big number. Okay, big and even. I don't know. It's B. I don't know. I just make up a set called B. And first, we know O and B are mutually exclusive. The reason is the interset is empty, or in the other word, there's no common outcomes, right? If O is true, B cannot be true. If B is true, O cannot be true. Okay, that's called mutually exclusive. And probably you will see E and B are not mutually exclusive, right? Because they have common element 4 and 6. Okay. And the next thing to talk about is collective exhaustive, right? So we have OPBR collective exhaustive because we go through the sample space. Okay, you can always find one in OPB, right? Because 1 is in O, okay? 2 is in P, 3 is in either O or P, 4 is on B, 5 is on O and P, 6 is on B, right? So everything is there. And we will say E and O are mutually exclusive and exhaustive. So E and O is a partition for sample space, right? So because you union them in the sample space, you intersect them, it's nothing, right? They are both mutually exclusive and exhaustive. Okay, so it's very important because the partition idea is a lot of formula relies on that. Okay, so you have to know what to mean by partition. Okay, is that okay? Is that fine? Okay. So for those who are from QFN, I mentioned always QFN because they will need it. The way we define probability later you will see is probably different from this stat. Okay, but the way axiomatic. Okay, because you learn if you learn they will from the measure theoretic idea. They got sigma algebra. But we're not going to that far. So we just at the axiom, then it's it. Okay, because probability technically means how you measure a set, and the problem is like you have infinite subset, then there's a problem. But we'll side chat the issue, but you will see in the technical slide. But that would be something that we'll talk a little bit more. So probability is a function that try to give events into number. Okay, what it means function is what is you give me something, I give you something. Okay, here is you give me an event, I give you a number. Okay, that's a function. Okay, probability is function. Okay, it's function. Okay, is that is the definition. Okay, this definition actually only appears in 1930s by Russian mathematician called Kolmogorov. This is a Kolmogorov axiom of probability definition. Okay, so if you learn probability history, actually start from Bernoulli, the Bernoulli family, and they started in 1600 when they talk about gambling. So mark those kind of people. It's 400 years ago. Okay, and mathematicians spent 300 years to come up with this definition. Okay, so of course that will be very condensed. Of course, the formal one will be very difficult, right? But we just learn from it, so don't worry. Everything will be very natural. The first axiom is very natural. As we expect, we have put restriction on what kind of number you can give me. You must always give me between 0 and 1. Okay, that's definition. And that coincides our definition in the classical sense because it's frequency, right? Where the frequency is always between 0 and 1, right? So that is this axiom 1 is very natural, right? Probability is a function. Okay, you give me an event, I give you a number, assuming I call probability. Okay, and I always give you a number between 0 to 1. Okay, and that's a minimum probability. The first axiom. We have 4 axioms. This is the first one. Okay, the second one is also very natural. Okay, axiom 2 is the sample space. You give me a sample space, I'll tell you 1. Very simple, right? Because it does mean that I know everything about the random experiment, right? I know everything, right? So that's nothing I don't know. Okay. You have to define properly the sample space. Okay. So that means that the idea of this is saying that we have a complete knowledge about what we're going to model. If there's no missing part in the model, okay, there's no surprise, as I said, right? There's no surprise from the outcome, all right? You're surprised this outcome actually comes out, but you know from the outset this outcome is possible in terms, at least in theory. Is that okay? Now, the next one, the last one, of course, this is the one that actually has a bite. Otherwise, what we're doing, right? Because the first two are pretty trivial. Okay. The last one is very simple. We have an event that consists of an mutually exclusive outcome. Okay. Mutually exclusive means that if O1 happen, O2 cannot, O2 cannot be O3. So one happen, the other will not, right? So one of them will happen. That means that the interset is empty set, right? That's what it means in the bracket. Okay, mutually exclusive. And the statement just means the following. Okay. And A, of course, is a collection, actually means the union of this, right? This notation actually means the following, right? Because it does mean the body, right? It says O1 union O2 union up to union ON, right? Or the union, okay? It's probability that you give me this event, the union of this outcome, which is mutually exclusive. And the axiom is basically assert, okay, saying it must be true that it will be sum of individual. Okay. In mathematics, it's called additivity, right? Adding up. Okay. And idea is the following, right? It will actually fit our intuition. I have a cake, birthday cake or a moon cake. Probably in this day you eat a lot of moon cake, right? It's a mid-autumn festival, right? What it means is no matter how you cut the moon cake, right? And you eat every single pieces, it's same as you eat the whole moon cake, right? Regardless of how you cut it, you calculate probability for each part, same as you calculate it as a whole, right? It is sum is equal to its part, sum of its part, right? The function of the probability will be sum of its parts of the probability, right? It's not more than, it's not less than, okay? Or in other words, it's a 1 + 1 = 2, right? Right? It's not 1 + 1 more than 2 or less than 2. Okay, you have a different parts, right? The probability whether you look at this small part and this small part add together, same as look at the same time. Okay, there's no strategy. There's the same. That means that one thing, divide and conquer the strategy is fine. Okay, you can look at small part, add up together. So that's actually the probability idea, right? Or you try to, as I said, the probability in terms of the modern language is a measurement, measuring how large is the set. It doesn't matter how you measure in different way. Okay, so that's what you mean, right? As long as they're mutually exclusive, you can just add them up. It's fine. That means the following: if you roll a die, the probability of getting an even number will be the probability of getting even plus, getting 2 plus getting 4 plus getting 6. Because even is equal to 4, 2, 4, 6, right? Probability even number will be probability 2 plus 4 plus 6, right? Probability odd number will be probability 1 plus probability 2, probability 1 plus probability 3 plus probability 5. Is that clear? Okay, it's not more than or not less than, so exactly the same. Regardless of what you do, as long as they're mutually exclusive, you can divide them into small part and do calculation. Okay, that is only 3 axioms. And these 3 axioms build up all the knowledge we know. Okay, so it's very simple. It's very simple, right? These 3 axioms. I think everyone will accept this. Okay, and this is the axiom that we build up all the probability rule that you learn. You learned that in your high school, right? Because some of you have learned probability. That's we will derive all the rule from the high school. Okay, but let's get started. So example, because the example will help you a lot. Okay, so we have. Remember, we roll a die, and do note that we are not relying random experiment. Okay, we are not doing random experiment. We are just define probability. Okay, probability function. You tell me what kind of function. As long as that function satisfies the free axiom, then it's a probability. Okay. And it's so flexible, right? So you fit every scenario. Okay, and then all the rules apply on those. Okay, first we have sample space 1 up to 6. Okay, and axiom 2, you must set we know everything. So probability of S is 1, right? Because it must one of them will happen, right? Axiom 3 said because this outcome are mutually exclusive, right? So probability S, which is 1 from axiom 2, is sum of the 6, right? So you can divide them into 6 things. Okay. So how can we know from that on? Okay. Now we define the die is fair. Okay, we define it. Okay, the die is fair, then we can say each outcome are equally likely, right? And you can solve the 2 equations, right? Because you can let this is x, right? Then this equation with 6x equal to 1, x is 1/6, right? It's actually by solving equation, right? Is that clear? Is it solving? Maybe I should put it there because in case you don't know, but because you assume that fair is x here, you have 1 is here, x 1 equal to 6x. That's why you get this one. Okay, it's not 1/6 by def. It's not directly. You have to calculate. Okay, it's by assumption. Okay, and that means that we know everything. You know how to calculate. Suppose I want to ask what is probability of even number, which is consists of 2, 4, and 6. Then you just add it up, right? Because that is axiom 3. Okay, so that means that we can here we have definition. We define the die is fair, so that's why adding x. All right, but you can reconstruct it, making different assumption. Maybe you can say number 1 is twice more likely as 2, right? Which is 3rd time more likely as 3, and so on. Already make some assumption. This is also a probability. Okay, and of course you can physically make this kind of this kind of die happen, right? But that means that everything we learn will be consistent of any real world scenario, right? As long as they follow this. Is that clear? Why we have to do this? Because we do not want to rely on the real world. Okay, of course, the real world can tell us what kind of condition to be put there, right? But we can always easily construct whatever we like. That allow us to study anything we want in terms of probability. That builds the foundation for the next topic. When a random variable, why the bell curve? Is there anything existing in the world as a bell? Not really, but anyway, we can make some assumption and we can see whether it's a good model here and there. Is that okay? So I hope I convince you why to do this, but this is all the textbook do this, okay? So it's not something I deliberately make you miserable by making more math, okay? Even in your very textbook, they introduce this, okay? So, I mean, that is standard. What I want to say is nothing very special here. And I said to QFN student, I mean, if you want further, then probably you have to learn the sigma algebra, those kind of things. But we're not going to do that, okay? The only thing that probably they would be concerned is, okay, it's very natural, right? Whole thing is equal to sum of its part. There should be no issue. Okay? The only issue for you to see why there's a problem is I cut a mooncake. If I find a number of cuts, it should be a non-issue. The only problem is you have infinite cuts. Okay? If you cut the mooncake into very small infinite cut, is it going to be sum of its part is equal to the whole? It's not clear. Right, there's a lot of, you know, that the math, if you try to learn math, go to YouTube, right? There are a lot of paradox of infinity, right? And the same goes on here, right? When you have this, is it going to be true or not? Okay, this is the real bite of this theory, right? If the real bite of this axiom is asserted, this is true. Okay, this is actually the assumption if you learn deeper probability. This is the only thing that is have built up the whole structure of mathematics. Okay, is infinite still whole. Okay, if you find I, it's very natural. Okay, but anyway, it's technical, so if you don't understand, it's fine. Right? But just saying that the only rule by the axiom 3 is the, and actually this is the axiom, the real axiom that actually people use in the modern mathematics. So this is the formal one. Okay, but anyway, we are not mathematicians. So, and the reason why infinite is important because next topic we'll learn continuous random variable, right? Because number is continuous, we assume, right? It's not discrete, so it's the infinite is there, but that is still whole. Okay, but anyway, we're business school student, right? So we don't really care about this infinity or continuous. We just continuous, whatever, just apply. Okay, but you do not know that there's something here. I mean, we'll leave it to a mathematician and statistician to do it. So why we take the burden to do all the proofs, so learn the definition, because of if you do this free assumption, we have a lot of property from probability we can apply. And because we axiomatic definition means that this definition, if as long as it's satisfied, this will apply. Right? So that means that I don't rely on doing the experiment to make it right. Okay? So this is the rule. The first rule is very simple. This rule is very simple. The complement rule, probably also learned in high school. It means that you can move to the other side, right? It means that for the A plus the A complement equal to 1. Right? The proof is very simple, right? Because axiom 3 tells you S is A union A complement, right? And they're mutually exclusive. That's why they add together. Okay? Of course, we don't care about the proof, right? But I tell you the example, you will see how it works. Okay? And probably you ask why we do that. The reason is sometimes you can't really go for complement. Go for A, you want to do the complement. Right? So it's this is the way we work on probability. Okay, so let's see the example. So this example would be, it's very simple, but illustrate the point. Okay, so I want to have a probability that roll a die equal to or less than, or a die less than 6. Okay, and you have to figure out the event that's called A event is less than 6. Okay, and then you probably have to count what the outcome less than 6, right? You have to count 1, 2, 3, 4, 5, right? It's a fair die, then the 5 or 6, right? Then this is how you can directly calculate, right? But sometimes you have to count, then it's a lot, right? So how can we do it? Is consider exactly the complement, right? Less than 6. In this case, it's just one thing, just 6, right? So just 1 minus 1 6, then we're done, right? So you can see that we don't do any counting at all, right? So the thing is much easier because A complement can be much easier than calculating A, right? So that's the idea. Okay, let me illustrate this from another point of view. Okay, so this is 6. I don't know what are the things inside, but I know outside I'm fine, right? I don't need to count how many of them are inside. I just need to know only one of them outside and total there's 6 of them, then we're done. Okay, so that's one way to do it, right? So technically it will apply to any partition, right? So I have a partition of the sample space, right? And I just add them all up, then it's 1, right? That is coming from the axiom 3. I'm not going to prove it, but this is an example that actually being useful. Okay, suppose you roll a die twice. Remember how many outcomes are there? 36, right? And you want to say what the sum of the 2 results is 11, right? How many of them you will count? 36, right? To figure out add every outcomes, what is add up, is it less than 11? Okay, your life will be miserable. I mean, of course, you can give it to your cousin. He has nothing to do, then he or she can do it, right? But if you want to do it, then how can we do that quickly? Okay, so the way we do is we define AI is the out event that sum is I. Okay, and in that case, we have A2 to A12 is the partition of sample space because and then two numbers up, either is 2, the minimum is 2, the maximum is 12, right? And when you have 1, when you have 2, even the 3, you can see as a 4. So they're mutually exclusive in the partition because either one of them must be true, right? Remember, partition is what? One of them must be true, and only one of them is true, right? 2 to 12 is already exhaust everything, okay? And why this is easier? Because it's asking the complement is 11 and 12, right? Because it's 2, it's asking what is less than 11, right? It's just union A11 and A12. And A11 and A12 is easy. A12 is just one outcome. 6 plus 6 is 12, right? And A11 is just 5 and 6 or 6 and 5, just 2. So just 3 outcome out of 36. So just 1 minus this and we're done. Is that clear how this being worked out? Rather than you count 33 outcome. So that is usually the way you proceed in probability, right? Sometimes very difficult to calculate directly. You have to do it indirectly, right? I think I mentioned this analog, right? So I suppose 10 years ago, right? If I see a beautiful lady sitting here, right? I'm not going to ask her telephone number directly, right? I can't do that, right? That will become a weirdo, right? So I will do other way around, right? Maybe I ask his friend to give me or to give her a flower and then ask, right? So that's a indirectly. So to do it directly is very complicated. To go indirectly. Okay? So the same thing happened. Now we have this rule we call the addition rule. Okay. And this rule actually relate what we call AND and OR. So relate how we do interset and union. Okay. So A union B axiom set if they're mutually exclusive, you can just add them. Right? That is what it said axiom. If they can't happen at the same time, just add, right? There's no overlapping. So the question is, okay, if they overlap, okay, how do we do? Okay, the activity addition rule means you have to subtract the intercept, okay, or is adding minus the, okay. So this rule looks crazy, but this is what you learn from the kindergarten. Okay, I convince you this is something you learn in kindergarten. Okay, you learn it, so don't worry. It's a kindergarten thing. I convince you quickly. Okay, and of course this here, this technical means you just swap the end and the beginning, you get the same rule. Okay, because some book use this one, but I think it's more natural. But why is the case? Okay, let's go through the example. I convince you this kindergarten. Okay, we have a diagonal ones. Okay, and what's the probability to get an even number or number greater than 3? Okay, of course. You can easily do the calculation. You can do directly. Okay, this one directly is also very easy because A or B is what? Right, even number or 3. You can just look at it. Is it? Maybe you just start from the beginning, right? Easier, right? Even number are 2, 4, 6. Greater than 3 is 4, 5, 6, right? So what is the union? Or it just writing everything there, right? 2, 4, 5, 6, right? It's 4 over 6, right? It's 2, 4, right? You can do directly, right? But let's illustrate you how you can do this. Okay. Now suppose we can do intercept. Okay. Intercept is find the common element there, right? Only 4 appear both, 6 appear both. This is how you get the 2 element here, right? It's 2, right? Because this is the intercept, right? So what you're going to do, the probability will be, you just probably A from here, right? And B from here, right? And you subtract the green there, okay? That's how you get, right? You just A plus B minus A intercept B. It's a union, right? So now I convince you this is the same answer, right? But I now convince you this is what you learn in the kindergarten. Okay? Remember what is A and B here. Okay? A, right, has 2, 4, 6, right? Has 3 elements here, right? And we have B here, 4, 5, 6, right? And we have 10 here, right? Where 4 and 6 is A and B, right? And what we want to ask is, what is maybe it's flat, right? What's A union B, right? Which is 4, which is 2, 4, 6, 5, right? Let's look at the thing you learned in kindergarten, right? Now we have a red circle, right? And now a blue circle, right? And we have a pink thing, right? We have a black, right? So remember kindergarten is red plus blue, and you try to subtract from the pink is equal to this, I don't know what shape it is, right? So you add them up, you take out the overlapping area, right? Then it's what we want to get, right? It's kindergarten what we learn, right? You want to calculate this area, right? This area, you take this and this overlap, take it out. That's it, right? I think you learned in kindergarten, right? Is that okay? That is what it means. Okay? Hope this convinces you. Now this is I think we'll cover this example, okay? And we should end today. So this course correlation table, we covered this last class, okay? And so the first class, what we have is 80 students, and we divide them either male or female, pass or fail, right? So here we illustrate how we can use this to do N, okay? So the question is, what's probability that a randomly drawn student is either male or pass the exam, okay? We want to use this probability rule to do what we want, okay? So remind you that what does that mean here? When I have a 15 here, means this guy is either a male who passed the exam, okay? It's N, okay? It's an intercept in this idea, okay? 15 students there, okay? And to just remind you again, what do you mean by this 20? 20 means that 20 female that failed exam, okay? And here we have the total, which means that in total the active student, okay? So now quickly finish this example, and what we have is probability male is what? You have 40 males over 80 because the total, right? So half of the time you randomly draw a student is actually a male, right? And similarly, how likely you get a student who's passed is just this total over 80, right? And as we said, this number 15 is the male and pass over 80. So this number. Now, the next bullet point is trying to give you the idea why we have male or pass, right? Male or pass will be just male plus minus male and pass. Right? So give you the 0.705. Okay? So that's the answer, right? So if you give me 3 bullet points, the first 3, I give you the 4th one. Okay? But if I also get the raw data, the table, we can also calculate this easily. Why? Because how many people are male or pass? Coming from here, right? So it's 60 over 80, so it's 0.75. that clear? So that's what we want. Oh, I still have 5 minutes. Let's very roughly tell you the next rule, because I think that will a little bit interesting, but probably we'll revisit again, but quickly. So this rule again is not difficult, but graphically it's very simple. So you just say A can be decomposed in A intercept B and A in B complement. So it's A and A with B and A without B. Okay? So graphically it's very simple. You draw a graph. Let's look at the graph, because this rule is very simple, so I think it's okay we cover it here. Okay? A is the red one, B is the blue one. Okay? So it says essentially say B cuts A into the part where with A without B. Right? This part is with B, this part without B. Right? So whether A is together with B or without B, right? So that's why you can say probably A is A with B plus A without B. Okay, that's very simple. Okay, so that is the total probability rule. Okay, and this also apply when you have a partition, right? If A, your B probability will be B with A1 with B A2, A3, A4 up to AN. Okay, so that's a rule. Okay, and maybe I talk about one more, because we'll go again because we'll go back this again next class, but I want to talk about this as well because of time, right? So this one is very simple because there's nothing new to learn, just definition. So this is another way to define probability in the traditionally. So you probability is something actually mathematician invent, but before mathematician actually people call about odds. Okay, odds is indeed as a ratio of probably A over A complement. Okay, if A is 1/2, odd is 1, right? So it's actually, if you try to plot it in the diagram, if you odd ratio and this probability A, 1 is here, something like this. Okay? And odd is simply just, I mean, this is very small, I think until 0.9, something like. Okay, it's simply just like a transformation, another way to tell. Okay, and probably why you would consider odd ratio, because odd ratio is still used in betting or gambling industry. Okay, and we'll cover more in the next class, but this number odd, and you do notice that in the slide I have 2 odd, one is in favor, one is against. If people often didn't mention what they're talking about, but always when this is the case, they always mean in favor. Okay, but why is it important? Because odd is actually related to the odd we learn in gambling industry. Okay, and betting odd means 4 to 1, which means that if you win $4. If you lose $1. Okay, and a fair bet means that is inversely is a fair. Okay, give you an example. We'll revisit later. Don't worry, quickly. So roll a die. Okay, of 6. If you 6, you win. Okay, and what's odd ratio? Is 1 to 5, right? Because 1 time you win and 5 times you lose, right? And what's a fair? Means whenever you win $5. When you lose $1. And if you keep doing this, you can't win any money, you can't lose any money. That's called a odds. Fair bet, fair odd. Okay, don't worry, we'll cover this again on Friday, but just give you some idea what we're doing. Okay, see you on Friday.
Please.